All right, Ina, you ready?
Yeah.
Cool. All right, everyone, welcome back. This afternoon, we'll be starting with Ina Petkova, who will be telling us about Annular, linked Floer homology, and GL11.
All right, thanks for having me, virtually having me. I'm sorry I missed lunch for that reason, but I'm sure it was great. It's still been nice to participate. It's been nice to see people. I wish I could be there in person. So I'm gonna tell you today about an ongoing project with Andy Manion, who I think is here. I just saw, yeah, there you go, Andy's here, and Mike Wong, who is not here, about linked Floer homology and GL11. And I think some people in the audience may have heard this this story before. So, but feel free to ask questions. I'm just gonna kind of try to give a general idea for what we're working on without a ton of details. Who knows? So, I mean, maybe one motivating thing here to start asking questions is this just general idea of knot invariance and these two different worlds that I think pretty much a lot of us work in. So starting with polynomial knot and link invariance, we have the Jones and the Alexander polynomials as examples, and their categorifications, Kovanov homology and knot Floer homology. So there are different ways you can think of these, but you could think of them as bigraded groups or filtered chain complexes, bigraded chain complexes. And so when you take graded Euler characteristic, you get to a polynomial. They're way stronger than their Euler characteristics. They tell us a lot about the knot. We've already heard examples. And there is a cat, Sam. Sorry, Samantha Allen has a cat. Okay. And so, but they're defined a priori in these two very different ways. And so I think a lot of, I mean, you could kind of try to understand things about knots by studying either, or you could try to use the power of one in order to conclude something about another, and so on. So the Jones polynomial and also Kovanov homology, they kind of come from representation theory, I guess. And knot Floer homology was originally defined as an extension of Hager-Floer homology, which is more or less a Lagrangian Floer theory for that happens in a high dimensional space associated to a knot. So very, very different constructions, but a lot has recently been discovered about connections between the two theories. And I think part of our motivation, well, Andy's here, so his might be different, but all three of us maybe come from different places, but maybe my motivation is just to understand the connections between these two worlds a little better. And so I'm going to backtrack a couple of decades now and go back to how are these polynomials defined? There's many different ways, and I'm just going to focus on one coming from, I guess, quantum field theory. So what is the idea here? Suppose you have a knot or a link, and you want to make a polynomial for it. And here's one approach how you can do that, going back to the 80s. So you're going to draw your knot, and you're going to think of it as being born from nothing. Look at a diagram of it and think of it as being created from nothing by attaching a bunch of cups and caps and crossings here and there. Okay, like that. And so this is what we're going to do. We're going to fix an algebraic choice here. We're going to fix a quantum group. And we're going to fix a representation of that group, quantum group. Okay, and so we're going to cut our knot or a link into elementary pieces, as we just said, cups, caps, and crossings. And we're going to do the following. So I think we've all seen this in some version or another, but we're going to associate to the empty set level of slicing the ground ring. So in our case, CFQ for our quantum group. And at any given level, what are we seeing? We're seeing a line intersecting the link in a bunch of points. And if the points are a place where the link is pointing up, we're going to associate the representation that we've chosen. Let's go with V. And if at that point my knot is pointing down, I'm going to associate the dual of that representation. All right. Or if you're lazy, just think vector spaces for a moment, and that's going to work just fine for a second. And so I'm going to tensor them as I see a bunch of points. So here's a tensor product of representations. And then, so what should I associate to the cobordisms between the points? In other words, what should I associate to a tangle like that? I'm going to associate a map between representations. Okay. So this is the general idea. So if you have a closed link and compose all the maps in order, you're going to get some map from C of Q to C of Q. And that map is going to be a scalar of the identity. So it's going to send one to a polynomial. And if I've done my job fairly well, I'm going to create something that's invariant under how I've drawn the link. So it's going to respect certain randomized moves and so on, and should give me an invariant of the link. So here's my one being sent to a polynomial. Okay. That's how, for example, if you take SL2 and the standard two-dimensional vector representation, you get the Jones polynomial. And you sort of, with some technical blank boxes that I'm not going to quite talk about, but in a sort of similar way, you get the Alexander polynomial. Okay. So this is the background story. And I mean, a very general kind of not very well formulated goal or a driving force in new math is, well, we want to categorify this construction. We want to replace these representations with categories, and we want to replace the maps between them with functors between categories. Okay, and get something stronger. Okay. Let me just pause for a second. So is the writing still okay? Is the volume still okay? Maybe someone from the room can shout out a yes or a no.
Right to the right of the letter V, you wrote sort of in gray.
Yeah. So I told you, well, I wrote it very dark so that you don't see it and don't ask me about it, but I guess I failed. So the reality is that if you apply this exact construction using J11 and V, and you get from the empty set to the empty set, you're going to get the map you're going to get is 0. But if you just slightly tweak the construction and think of your link as a 1-1 tangle, you're actually going to get something from V to V that's also going to be a scalar of the identity, and that scalar is going to be the Alexander polynomial. And we don't want to go there right now. But that's what the sort of stands for.
My real point was that you did a good job making that dark enough that most of us cannot read that.
Oh, damn it. And still you read it and sidetracked me. All right. Thank you. So it's readable. Great. All right. So this is where we come from. I mean, this is something Jones and Alexander have in common. That's one common way to start building. Okay. And so where can we get from that? Let's talk about, we said Knot-Floer homology is a categorification of the Alexander polynomial. Let's talk about its version for tangles. So just to go a page earlier, composing a bunch of slices gives me a tangle. And I want to ask, well, what is the kind of thing that should categorify this map on representations? And so this goes a few years back to work we did with Vertesi. So we defined the bordered Hager-Floer theory for tangles, which recovers Knot-Floer homology. So the rough idea is everything in a black box, but this is the kind of objects we study. So to a sequence of points, so see the picture you had on the previous page, I'm just rotating it 90 degrees, maybe clockwise, just to make it more convenient for me at the moment. And so here's your sequence of points. I'm going to associate to that, we associate to that a differential graded algebra. And I want to strip off as much notation as possible for the remaining 45 minutes. So I'm not going to orient my tango. I'm just going to think of dots and just count how many M of those we get a differential graded algebra AM. But in reality, we have everything oriented and we have slightly more elaborate structures. And so I have these differential graded algebras for the boundary. And so if I have a tango, I'm going to associate to that tango a differential graded bimodule over these two algebras. Okay. And I'm going to give a little glimpse of how this construction goes in a moment, but it's Hager diagrammatic in nature and very just basically an extension of non-floor homology. And so just quickly what this is, in some sense, you get an invariant of the tangle. We'll get to that in a moment. When you concatenate tangles, that corresponds to taking a derived tensor product of bimodules, okay? And when you have something that actually has no boundary, you recover link floor homology. One way to say that is that you get two copies of link floor homology off by one homological degree. Okay, so I said in a sense, so what do I mean by that? We have, just like in not floor homology, we have a tilde or hat weaker version and a minus version. And we can show that the tilde version is an invariant of the tango. There's very strong evidence that the -1 is an invariant of the tango as well, but there's no well-developed analytical construction for that. So one option is to finish the proof combinatorially. Maybe any questions so far? All right. So that's what it is. Here's the promised glimpse at how it's defined. We use what's known as bordered Hager diagrams. So just like you can have a Hager splitting for a 3-manifold and have two types of curves that tell you what the compressing disks on each side are, you could do that in something with boundary. So the rough idea is here's a diagram. So it's a surface, it has some genus, it has boundary, and that diagram somehow specifies whether you want to think of it as R2 cross I. I would suggest you think of it as something compact, so S2 cross I. And in it, you have base points, and so you can connect them to each other in various ways to build a tangle. There's an upcoming slide for that. Okay. And so what we do is you look at the surface and you look at sigma cross I cross R, and you count holomorphic curves there with certain asymptotics, just like one would in bordered Hager floor homology without having a one submanifold in it. And if you don't know what that is, I'm going to give a glimpse of what that is as well. So here's the rough idea. I'm promising here a bimodule over two differential graded algebras. The generators of that bimodule are going to be sets of intersection points between red and blue curves, so that there's exactly one intersection point on every blue. I'm kind of highlighting randomly just for a visual effect, but that's not a thing. So there's exactly one point on every blue curve, and there's exactly one point on every closed, on every circle, red circle, and up to one point on every red arc. Those are going to be the generators. And so it's a differential module. So it's going to have a differential on it, and it's going to have an action of the algebra on it. And the differential is going to count rectangles on the diagram, kind of like in grid homology. And the algebra action is going to record how half rectangles interact with the boundary of your diagram. So that's the general idea of what this construction does. Here's a, no, I'm very self-conscious about the size of these things, but I'm going to go with the assumption that everything is readable. So how do we recover the tangle on a bordered Hager diagram? We had all these X and O markings, and we're going to connect them away from the one type of curves, away from the other type of curves. And the ones away from the blue curves are going to be going over the arcs that are away from the red curves. So I'm going to create over and under crossings. Okay. And when there's nothing else to connect, because there's a single point in something co-bounded by red curves, I'm just going to go to the boundary like that. So this green thing is a tango, and I've just drawn it on the bottom a little cleaner. There's another reason I drew it on the bottom a little cleaner. This definition of generators and differentials on a Hager diagram could be translated into a strand diagrammatic language. So You see how your Hager diagram is sort of made out of a sequence of grids? You could straighten these out and just think, well, all right. So maybe I do want to zoom in. Okay, so I will zoom in. And so here's, for example, an intersection point between the lowest alpha curve, red curve. This is not working. Eh? Okay, here's an intersection point between the lowest red curve on this grid and the third in height or concentrically blue curve. And so that intersection point, instead, I could draw something that connects, well, this lowest red dot stands for the lowest red curve, connected to this blue dot, which stands for the third blue curve. So all of a sudden, dots become strands. You can think of it as permutations. And in that language, the differential, which was supposed to count rectangles and move us from one generator to another, is instead gonna look at strand diagrams, and whenever it sees an intersection, it will try to smooth it. And there are gonna be certain relations. Say you smooth something and you get a double crossing, you should set that to 0. I'm being extremely hand wavy, but I just kind of want to give a visual picture of how maybe visually pleasing it is to define something like that. It's completely combinatorial, although kind of big, but you can teach it to an undergrad or a computer without too much trouble. Good luck teaching them the category theoretic stuff, though. Okay, and so the algebra is defined in a similar way. We said that we're going to record where on the boundary of the Hager diagram partial rectangle is going. And so the generators of our algebra are also going to be given by strand diagrams, just kind of thinking of here's a strand diagram and it projects to sort of this. Okay. Multiplication corresponds to concatenating pictures. The differential corresponds to smoothing. So I'm fully aware I'm being hand wavy. We're not going to need a complete definition to process anything of what I'm going to say. So I hope that's okay. Okay, but that's the rough idea. Here's an example. This string of white diagrams that I'm highlighting is an example of one generator of this module. And the fact that I have a rectangle going here that goes through the boundary means that if I multiply this generator, let's call it X, by this algebra element, let's call it A, I get this new generator on the bottom, yellow, which is obtained by sticking in the diagram for A into the very right piece for X and just drawing what that becomes. Okay. So let's go to this promised GL11 relation here. So before we go to anything annular, we show with Ellis and Vertesi that this construction, in a sense, categorifies the so-called Reshetikhin-Turaev construction we saw 15 minutes ago, the one where you slice up a tangle, a knot into tangles, and you build into a polynomial. So what do we mean by that? If you look at the Grothendieck group of the category of modules over your algebra, it turns out it's got for a basis the images of certain modules, which in a sense correspond to a well-understood basis for the tensor of the representations that were going to be corresponding to the ends of the tangle. So the notation is a bit heavy, but there's a well-understood correspondence on the level of bases between a tensor representation for the boundary of a tangle and between the Grothendieck group for of modules over the algebra for the boundary of the tangle. Okay, and with this correspondence in mind on the level of basis elements, if you look at the bimodule for a tangle, Well, it gives you a well-defined, it gives you a homomorphism on the level of Grothendieck groups. And it turns out that that homomorphism is exactly the Reshetikhin-Turaev map for that same tangle, right? We get a map from a tensor of representations to another tensor of representations. And it turns out it gives us the map for the same exact tangle with just a single trivial strand tagging along for fun. Okay. Okay, well, so far this is a big word to use for these two results, right? So another little thing we do is, and this is still a big word, is we construct functors which correspond to the action of two special elements in quantum GL11. It corresponds to their action on representations. And so I'm going to go into detail a little bit on what that is. All right, so not going to fully define what quantum GL11 is, but what we really care about at the moment is that it is generated by two special elements that we're going to call E and F, Z plus Z many generators that we're going to label as Q to the maybe pair of integers, and it's subject to a bunch of relations. And I've spelled out below some of these relations. All right, and so that's your quantum group, and it acts on your representations. And so the Reshetikhin-Turaev construction gives you this equivariant map. So in green, I guess, is your quantum group. And for example, one relation is that E square is 0, F square is 0, EF plus FE is 1. And E and F commute with the Reshetikhin-Turaev map. Okay, so that's the before, or that's the downstairs situation. And so with Ellis and Vertesi, we define lits of these E and F elements. So we define explicitly actually bimodules so that they commute with Tangle Floer homology, which I was calling CT before, and for some reason on this page you see CFT. And you know, E squared to 0, the categorified version is E tensor E is homotopy equivalent to 0, and so on. And you have a triangle, which is the lift of the relation EF plus FE is 1. Okay. Okay, so I'm about to start telling the new story, and maybe it's good to pause for any questions. Okay. All right, well, so not Floer homology, this is how it started on my end, all of this. And so like just kind of a general question is then, well, we've built all this, can we somehow get ourselves a GL11 action on, what is this? This is just maybe just think of it as a group or a vector space, whatever you like, on link Floer homology. And the quick answer is I don't quite know. But what we can say is that in the annular setting, there's something we can say. And so maybe one point of comparison is a similar result of Grigsby, Licata, and Verley for sutured Kvanov homology. So if you have a tangle and for SL2. Okay, so what do I mean by annular setting? Well, first, just more abstractly, suppose we have a two category. So in our setting, our objects are going to be differential graded algebras. Right, that's what we're associating to the end of a tangle. The one morphisms are going to be bimodules, and the two morphisms are going to be certain bimodule homomorphisms. Then if you have something like that, you can apply Hochschild, you can take Hochschild homology, I guess. And so if you have a one morphism, so if you have a bimodule over the same DGA on the left and on the right, you can get from that the Hochschild chain complex, right? And if you have a two morphism, that also corresponds to a map on chain complexes. And so one thing we show explicitly is you have Tangle Floer homology, which is a bimodule for a tangle. If you take its Hochschild homology, you what is the chain complex you get? You get exactly the annular link Floer homology of, here's your tangle, of the closure of that tangle. And so I'm saying annular, you get the link Floer homology of the closure of the tangle together with the, I'm going to call tangle axis, right? Like that. So maybe this goes green and like that. Okay. Sorry, bear with me. There you go. And so thinking from that perspective, this is the work that's ongoing with Andy and Mike Wong. So now we have the annular link Floer homology of the closure of the tangle together with the tangle axis. And we show that, so I'm hand waving a bunch of things. So we somewhat tweak the definitions of these ENF bimodules to make them a little more sensible. And from these bimodules, we get chain maps, little e and little f, on link Floer homology that satisfies certain properties. So, for example, the square of V is 0. That now looks familiar. The square of f is 0. EF plus FE is the identity. And these ENF chain maps, they commute with what one would want to say are the tangle cobordism maps. Okay, so that's the first part. And the second part is that, well, we kind of want to have a geometric understanding of what these chain maps are. So we can show that on the level of a Hager diagram, these actions, ENF, correspond to certain base point actions. So of corresponding to base points of this tangle axis A. And so the idea of our approach uses a construction on bicategories known as horizontal trace, which was applied by Belyakova, Potira, and Verily to get a quantum SL2 action on annular Kovanov homology, for example. A couple of cautions here. So first of all, that in our setting, we don't quite actually have a bicategory. We have, I guess, a sesquicategory. So what that means is that the interchange law for two morphisms doesn't quite hold, but it holds up to homotopy. And another caution is there is no well-developed theory of cobordism. So that's why the word candidate cobordism maps these two statements. All right. And so maybe about 20 something minutes remaining, I'm gonna mention quickly what this horizontal trace is, and then I'm gonna get a little more concrete into what we do. So here's a bit of a heavy slide, but let me just say that if you have a bicategory, then the horizontal trace of it is a new category whose objects are one endomorphisms, okay? So like that, and whose morphisms are pairs of one morphism and a two morphism subject to some relations. And this just sounds all very vague, but I've kind of tried to sketch it out graphically below. And maybe this reminds a little bit of Mike's pictures from yesterday morning, except he wasn't labeling his two morphisms. So instead of staring much longer at this, I'm going to get a little more concrete in a moment. But so suppose you have a one morphism. So in our case, I'm going to think of, suppose I have an AA. So suppose I have a bimodule for a tangle, and I have the same DGA on the left and on the right, so that it's a tangle that I can glue to itself. Then if I can glue it to itself, maybe I can represent that one morphism graphically as a closed circle in horizontal trace. And if I have a pair of two morphisms sigma between PF and maybe some GP, right? So these were the morphisms in horizontal trace, then maybe it would make sense to also draw it graphically on a cylinder, right? So there we are. Except, what am I gonna do with these ends? I could close them off and just say, I'm gonna graphically draw it this way, but I wanna make some kind of more intelligent sense of that picture. I mean, what do these really mean? So if your element P has a left dual, then we can think of these as the evaluation and co-evaluation maps. So just a quick reminder what this means. So a one morphism F is a left dual of, F star is a left dual of F if we have certain relations. This is also something that Michael drew yesterday. So I'm just kind of skipping it very quickly, but you can think of it as graphically like that. So in his setup, everything had both left and right duals. In our setup, it's not going to be like that. Okay. If I'm in a situation like that, then this horizontal trace construction is something that I can think of as a sequence of very specific maps. Okay, so maybe I want to zoom in on this picture. Okay, so think of this as, right, so I had a one morphism, maybe I have a bimodule for a tangle, and from it, I get an object in horizontal trace. Very specifically, I'm going to take the Hochschild homology of the bimodule for my tangle, and that becomes a chain complex. And I want to slice this cylinder corresponding to a two morphism into a bunch of maps. And at each level, I'm going to have a map. So what do I have? So I have the left dual of P, then F. And so I can take the Hochschild complex for that guy. And so I have this eta, right? That's my co-evaluation map. And I could tensor it with the identity for F. I could continue. So here at this level, I have sigma, my two morphism. And so I just take I'm just applying the Hochschild functor here, and I see what I get. And at the next level, this white strand that represents P dual wraps around the cylinder. And I've denoted that as theta, but that is just Hochschild slide rotation, whatever you want to call it. And at the end, I wrap up with evaluation. Okay. And so I compose all these maps, and it gives me a very well-prescribed recipe to get something, well, to get a chain map between the starting and the ending Hochschild complexes, a chain map that corresponds to this two morphism sigma, well, to rather this one morphism in horizontal trace. And so this is the kind of construction we're going to apply to Tangle Floer homology in order to really understand what we have. So first of all, what is that construction? So what are we going to do? First of all, it turns out that these bimodules for E and F, they do have adjoints. They have left adjoints. And what I've drawn here is just explicitly their Hager diagrammatic description that we have. So here's a Hager diagram for E in the case of where your tangle maybe has, sorry, my highlighter doesn't work. So here's a Hager diagram for E in the case where your tangle has maybe two strands as ends. And here's the left dual of E, then the left dual of that guy, the left dual of that guy, and then the left dual of the final guy is E again. And you could translate that to strand diagrammatic language if you prefer. And so you could look and diagrammatically, you could come up with maps that end up satisfying the adjunction rules. in order to see that these are really left adjoints, duals. Okay, so that's a step we need. And then how are we getting this desired GL11 action? So let me go back to these. So now we have these 4 different bimodules. So that cyclically each is a left dual of the previous one. And we showed that if we use them in that cylinder picture as when I go back to it. So here's your cylinder. And this F here is going to be the Tangle Floer homology of a self-global tangle. And this little P here, I'm going to maybe plug in E, the bimodule for that kind of lifts the E from J11. And the sigma 2 morphism here is going to be the map that shows me that E commutes with Tangle Floer homology. And so with that in mind, I'm going to apply this construction and see what happens. And what happens is a chain map on the Hochschild homology of F, because I'm still going to have F here. And that map is the little E that we're going to see 2 slides later. Okay, and so by doing that computation, we get these 4 different chain maps on annular link Floer homology. And they end up satisfying the T square and F square is 0 and EF plus FE is 1, the identity. And like we said, we want to be a little cautious here what we mean. Okay. So here's the rough idea of how you see that. We need to prove certain properties of these 2 morphisms related to E and F. For example, we said that the EF plus F equals 1 relation in J11 lifts to an exact triangle of DG bimodules. And so what we need to understand is we need to understand the maps in that triangle. So we have concrete homotopy. Well, we have concrete maps. We have very concrete homotopy equivalences to prove that T tensor E is 0 and so on and so on. And we have homotopy equivalences from E tensor, the bimodule for a tangle, to the bimodule for a tangle tensor E, and so on. So, right, I guess I had called it sigma before on the cylinder, but this map. So we need to understand these. That's one step. And once we understand them, here's a little cleaner again. This is what we do. We have a bimodule, we take its Hochschild homology, and then here's an example of what happens if you think about E. You have this homotopy equivalence map, which we understand by looking at Hager diagrams, and you compose everything together and you get your E, which is a chain map from link Floer homology of T union the axis to itself. And so it's all very concrete and computable, but it's this general horizontal trace idea. Okay. So the fact that these actions correspond to base point actions is something we can just kind of see by picture in a moment. But I just maybe wanted to point out that once you have that, you can think about these relations we get, say EF plus FE is 1, as corresponding facts we know for Hager diagrams. Like if you focus on a Z and a W base point on a Hager diagram that are both for this unknot, the tango axis, then you know that counting curves that cross the one kind of point and then the other, and then going in the opposite order, gives you something that's homotopic to the identity. I think now the conclusion is that it's best to look at Zemke's paper for that. And so what did I promise? I promised that this is visible through a picture. So maybe I want to just kind of show on a Hager diagram how one can see those maps. So what you're seeing in front of you is perhaps you could think of this part is just sort of maybe black boxing a Hager diagram for your tangle T. And somehow you're seeing in front of you actually a Hager 1, 2, 3 quadruple that somehow encodes information about this bimodule E and about the tangle T and so on and so on. And so by counting in sequence certain polygons on that diagram, you see the composition of those maps from the previous page, the maps in this annular construction, okay? So here's an example. We said that E tensor Tangle Floer homology of the tango should give you Tangle Floer tensor E. And that for one reason or another is, I think you get by counting curves that go like that. So in any case, the maps we define, they correspond to counting certain combinatorial polygons on a Hager diagram. And if you're careful, you can encode everything simultaneously and just kind of show a bijection on the level of regions that are being counted between this simultaneous diagram that encodes the tango and E together and a diagram that encodes the tango itself. All right, well, we promised not Floer homology, so we're slightly modifying the Hager diagram so that we're kind of gluing the two ends together. Stop syncing. Okay, so we're gluing the two ends of it together, and with a little bit of a modification and inserting a bunch of base points in a couple of regions, we also get to track that tango axis. So for example, what I've shaded here is the sequence of the regions being counted in that composition of maps. Is a big polygon here that crosses once a base point for this tango axis A. Okay. And so this is kind of the argument by picture that you have this very neat Hager Floer description of what these four actions are. Okay, so I'm just going to stop here. Thank you.
Questions for you?
Maybe I'll just go back to this picture.
Yeah.
Given that there is this GL11 action on like open angles, like does it give you any sense of whether there might be some secret representation theoretic structure on just not for homology? Like, can we get any result that says, so like annular homology has SL2 actions, so you can sort of know the structure. Is there any sort of like structure of trapezoidality or
Maybe so with respect of this little one knot is all I can, I guess. But so here, one thing about, I can't hear who's asking the question, but I think I heard the question.
That was Melissa.
I'm listening. I was guessing that, but the question. So I think the thing is this EF plus FE equals 1 is not a convenient relation to use to track trapezoidality. Like you really want to be going through SL2 kind of business in order to, I forget how these arguments go, but you start chasing things around and concluding various inequalities because of what goes up one and gets killed on the way down, something like that, right? And I think this game is being like, the way to play this game is using SL2 for one thing. And somehow GL11 is gonna fail you a little bit. Second, if you get something trapezoidal by having that kind of business, I think you're gonna have trapezoidality with respect to the Alexander grading corresponding to this knot. So it's a bit of a letdown in a sense, right? You want to get something really cool. You want to get something about the whole tango, but
know like this, you know, like maybe not trapezoidality, like you know the structure of the irreps of GL11, and they are also nice, right? So like, what is the corresponding argument? What is the corresponding result that you get from knowing that you have GL11 representation?
Let's see.
I also don't know what I'm looking for, so don't worry about it. If it's not-
The last sentence I missed.
Oh, I said I also don't know what exactly I'm looking for or want as a topologist when I say this.
Yeah.
So it's okay if it's not something that people think about.
I don't know. No, I think, I mean, it's something to think about. I don't have anything definitive to say. I mean, I think, Andy, do you have any thoughts on that? I think what we want to be having, we don't have it. But
Yeah, I guess I agree overall. I'm not, I mean, so GL11, you've got these representations that are just 1 and 2 dimensional. So whereas in SL2, you could like find some big irreducible representation and then some other one, you know, that has length n or something, whereas and then you can maybe get like trapezoidality out of that or something. But in GL11, yeah, you just get it breaking into a bunch of 1 and 2 dimensional guys.
Okay. Thanks.
Any questions?
I guess just thinking again.
Yep.
Next talk in 30 minutes.